You can try to minimize that window.
Oh, right.
Okay, so we should get started. Okay, so welcome back to Astronomy Colloquium. And so this week we're pleased to have Brian Williams visiting us from the NASA Goddard Space Flight Center. Brian did a PhD at North Carolina State and was awarded an NPP postdoc fellowship at NASA, where he was until he was briefly at Space Telescope, but then has moved back to NASA Goddard. Brian actually got started working on infrared observations, he tells me, of supernova remnants, but he has shifted to higher energy photons now, to the X-ray, and he's been involved in a number of X-ray missions, including this one he's going to tell us about today, which I wasn't sure how to pronounce it, but I'm told it's like XRISM.
Correct.
Okay, so somehow the X sounds a little bit like a chi, perhaps. So maybe that's the way to remember it. Okay, and yeah, he's going to tell us about the exciting news that they have from this rejuvenated telescope.
Cool,
And,
thanks.
Can we do the lights? And then put on the camera lights.
That'll put everybody to sleep. Is that a good time?
Yeah.
Okay, thanks. Well, thank you for having me. It's been nice to visit and get multiple campus tours. I appreciate that. I think I've seen most of the campus at this point. As Tony mentioned, I'm here to talk about XRISM today. This will be a little bit different than a normal science colloquium. I will talk about a little bit of science, but I'm mostly going to be giving you the status of our newest member of our astrophysics fleet. We just launched about a month ago. So hopefully some of you saw the launch. If not, I have some videos here, including some you probably haven't seen before. So, oops, I have to click this now. Yeah, now that'll work. So what is XRISM? Well, it stands for X-ray Imaging and Spectroscopy Mission. That's an artist conception down there in the bottom right, but of course I'll show you the real thing in a couple of slides. The name of the game here is to do X-ray spectroscopy, which we have been able to do before. We've had missions like Chandra and XMM Newton that have been up for almost 25 years that do imaging spectroscopy. You've seen beautiful Chandra images. I don't think you have any up here on the walls. That one might be purple Chandra back there, the smiley face. I'm not sure. But of course, Chandra's been making beautiful images for nearly a quarter of a century now. That's an image of Kepler's supernova remnant, very high resolution. It can do spectroscopy, but that's what passes for spectroscopy in the X-ray world. Those are supposed to be sharp emission lines. They kind of get into like rolling mountains by the time you pass them through a CCD. XRISM will go to the opposite end of parameter space. We won't make a nice, beautiful image, but we'll make what actually is a real spectrum where you can really start to measure emission lines and absorption lines and do plasma physics, really put the physics into astrophysics. We won't, as I said, we won't make nice, pretty images like this. We do have some imaging capabilities, and I'll talk about that a little later. It is a NASA JAXA collaborative mission. JAXA is the Japan Aerospace Exploration Agency. There's ESA participation as well. Those are the Europeans. We have 2 instruments on board. Our workhorse instrument is Resolve. This is a soft X-ray spectrometer to provide non-dispersive high-resolution X-ray spectroscopy. I'll tell you a little later exactly what I mean by non-dispersive versus dispersive and what the capabilities are. And we have an imager, a soft X-ray imager with a 40 arc minute field of view called Xtend. You all are the first ones that I've given this colloquium to since launch. So I used to have to say scheduled to launch, and now I can actually say we're in space now. We launched just over a month ago on September 7th from Japan. The mission is to recover the science that was lost with the demise of Hitomi, which was the previous version of this mission that was launched in 2016. Unfortunately lost about a month into it due to an operations error. But as you'll see, we did get some science out of that. And the science we got was so compelling that both agencies, both JAXA and NASA, felt it was necessary to rebuild this mission. So in just over 7 years, we did that. We went from losing the previous mission to launching the new one. So a general outline here, these things will kind of mix and match, but I'll tell you a little bit about the history of how we got to where we are. I'll talk a fair bit about the technology that goes into being able to do this type of science. I'll, of course, talk about the science we'll be able to do. I still don't have any science results yet that I can share. We're still in the commissioning phase. We're still turning the thing on, figuring out how to fly in space. I'll give you an up to the minute, basically, status of where we are, and then talk about how this will affect the general community and all of you. So going back to Hitomi, launched in February of 2016. As I said, 38 days in, unfortunately, it was lost. But prior to that, it had been exceeding expectations and provided some spectacular spectra. We only got very preliminary observations of about a half a dozen objects. And we really only had one nice observation and a bunch of kind of ratty things that hadn't really been, calibrated. The instrument wasn't turned on all the way. But even with that, we got a fair number of scientific papers out of it. And we really got a brief glimpse into the power of a high-resolution spectroscopy in the X-ray band. This is an image of the Perseus cluster and the optical. When we look at it in the X-rays from Chandra, we see a little bit different picture emerge. And the optical, of course, we're seeing the galaxies, the starlight basically is what dominates that. And the X-rays, we see the warm, the hot intergalactic medium. When we looked at this with XRISM, this was the actual spectrum that we saw. So for those of you on Zoom, I try not to use laser pointer too much so I can follow along with this big bright line here at 6.5 keV is the ubiquitous iron K alpha line. Iron is a very prominent element throughout the universe. If you ionize it all the way up to hydrogen and helium-like states, you can get an electron that drops back into the K shell and emits this famous line at 6.5 keV that almost everything in the universe, if it emits an X-rays, probably emits that. And for comparison, if you pass it to the graphic artist and they make a press release out of it, and we zoom in on that, this is the iron line, the bright one here in the center. That red dashed line that we had there before, that's the previous best spectrum we ever had of the Perseus cluster. So dialing up the resolution by 2 orders of magnitude, you go from a gentle rolling hill that's supposed to be an X-ray line to something where we actually see real structure in that. And in fact, if we zoom in on it further, this is the actual image that was in the Nature paper from 2016. Again, this rolling blue line was the previous best spectrum, clearly a line. We can obviously see something there. When we looked at it with Hitomi, we of course see that this is not just one line, it's actually multiple lines for multiple different electron levels. So you've got the forbidden line and then the resonance line. The two in the middle are intercombination lines. Go back to your atomic physics textbooks and remind yourself of what those are. But the ratio of these lines depends on the temperature, the strength of them depends on the abundances and the densities and stuff like that. So as I said, really starting to do actual atomic physics here from a spectra. This purple hump in the middle, that's the response of our instrument. So that's basically our resolution. The fact that we see something broader than that means we really are resolving the structure of this line. And in fact, when we converted it back to a velocity, we found that the turbulent velocity in the Perseus cluster was this number here, about 164 kilometers per second. Previously, we really had no idea what it was. So as I said, we have some imaging capabilities, not great. We have about arc-minute resolution, but that still is enough for us to make rudimentary maps on redshift and blue shift, just where that line is. And we can sort of get an idea of the 3D sloshing motion. So this is obviously color-coded with redshift stuff moving away from us. Again, this is a press release image, so the units up here are not real physical units, they're in miles per hour. The blue shift stuff is stuff that's moving towards us, so we can sort of get a sense of how the gas is sloshing over huge spatial scales. This is 100,000 light years here, is this bar at the bottom. We had a few other results. Some of you may remember back in 2014, people had stacked spectra from Chandra and XMM of the Perseus cluster, and there was this little bit of overabundance at 3.5 keV that some people thought, could it be dark matter? There's a sterile neutrino that's theorized to exist at that energy. So it could be, we actually looked at it, that part of the spectrum. We didn't see anything there. Those are just various models that are overplotted, and none of them seem to be consistent with the data. So it doesn't look like that was a dark matter line, but I'm told by the people that do this stuff that there's always some corner of parameter space that we haven't explored yet. So we'll go a lot deeper on more than one cluster, and we'll find out if there are other lines. This is a terrible spectrum, but that's because it only has 19 photons in it. This was a very brief pointing that was not pointed in the correct place, not nearly up to full capabilities yet, and it was very, very short. But this is a obscured high mass X-ray binary, and you can actually count the number of photons in that. It is 19. Even with just that, and with that terrible fit, we set the record for the best line width of the iron K alpha line for an object like this. Note the error bars there are huge, so this is kind of scraping the bottom of the barrel for science that you can do after a mission goes, unfortunately, flying into pieces. A cool thing, though, that happened was we pointed at a couple of pulsar wind nebulae. One was the Crab Nebula. The other was this one that was G21.5. This is the pulsar wind nebula in the center, the supernova remnants surrounding it here. And we found two potential absorption lines that we don't know what they are. There's one here at about 4.24 keV, another one at about 9.3 keV. The obvious interpretation there is, well, probably just instrumental artifacts. We didn't even make it to the calibration phase. That might be true, except that the bottom line is the Crab Nebula, and we didn't see anything there. So in other words, look at the left. This is the Crab Nebula. We see nothing there. In G21.5, we see, don't worry too much about the black and the red. That was just a little bit of filtering that was applied. We do see something that looks like an absorption line. So I don't know what it is. My guess is it's probably still some sort of instrumental artifact that popped up in one place and not in the other. But again, this is a type of source that we'll go back to, and we'll be doing all sorts of this stuff. So when we have now capabilities of doing actual spectroscopy, we're going to find lines that we don't know what they are. So how do we get to XRISM? As I said, JAXA came to NASA and said this is still a high priority for us to rebuild this mission. They met with high-level NASA officials, all the way up to the administrator, I believe. We agreed. We said, we'll be happy to partner with you again on this mission. We sort of restructured the organization a little bit. There's a little bit more talk between the two agencies as opposed to the previous one, where it was just kind of us delivering some hardware and then kind of stepping back. That shouldn't be construed as oversight, because it's just more of a collaborative agreement now between the two agencies to have a much more back and forth how this will work. So it was first named CHARM, X-ray Astronomy Recovery Mission. That was just the working title. In 2018, we renamed it to XRISM. So I don't know if this will come through online.
Flight mode on. The flight mode is on. The thermal back switch has been activated. Main system 準備完了. All systems are go. Main engine start. The main engine of the mission. For the BS that you thought solid booster ignited. Lift off. プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th, Japan Standard Time.
Minutes. It's online. You can find it, download it, watch it. It was a perfect launch. We were aiming for a circular orbit at 550 kilometers. It's just a low Earth orbit, 31-degree inclination. That's the latitude of Tanegashima Space Center. They got in the orbit at 577 kilometers. Higher is better in this case. It'll last longer. And the eccentricity of the circular orbit is accurate to, I believe, the 5th decimal place. It's like 0.0000, and then I think the 5th one is the first one that's not a zero. So flawless launch. This is another video. This is actually two videos put together, one from each side. You'll see the two boosters here. These are the two boosters, the solid rocket boosters that are dropping off. That happened just a couple minutes into launch. This next one I'm gonna have to play a couple times because it goes really quickly, but you'll see if you look at the picture up on the left, the bottom part, this is the rocket with all the rocket fuel. This is the fairing where the instrument is kept. There's a seam that runs right down the center here. The fairing is basically put on in two pieces like this. That at some point has to come off when you're in the atmosphere, when you're out of the atmosphere, that drops off. Unlike the boosters, though, you don't just want that casually dropping off, because what if it hits the instrument on the way down? So it basically explosively is blown off of both sides. So you'll see this, watch quickly. There it is, and there's the sun. So that video starts, like I said, I'll play it a couple times. Video starts with the fairing on. We are basically inside this encapsulated cylindrical thing. And you'll see there's one frame where it splits, and now it's already gone. And there's the sun. But the coolest video of all is at 14 minutes, 9 seconds after launch. We separated. If you watch the JWC launch a few years ago, you remember a video like this. Theirs was really cool because their solar panels started to deploy immediately. We actually didn't deploy our solar panels until one orbit, and so we don't have the cool effect that they had of. But it's basically the same video. So probably the last time we'll ever actually see it, whether with human eyes or with a camera. So, as I said, these videos are online. If you go to the JAXA Digital Archive, you can download them for yourself. So getting back to the technology about this, just a real quick primer on X-ray. Yeah. Yep. 577 kilometers above the surface of the Earth. The little ones that drop off fall back down. The main rocket, they just stay in orbit. Yeah. That's a discussion over dinner. We should probably start doing that someday, but as of right now, we don't have a great way of doing that. Quick primer on astronomy hardware. We do not use normal incidence mirrors like JWST or Hubble does. Throwing an X-ray into a mirror, it tends to just penetrate. I was explaining to some people at lunch. It is actually possible to do normal incidence X-ray reflection, but it is very limited to basically one band at a time. So you just get a monochromatic mirror. Instead, if we can't, if we drop a rock into a pond, we've been expected to bounce back up, but we can skip it across. And that's the way X-ray mirrors work. They work like the ones down at the bottom where they're grazing incidence mirrors. You still have to have two of them. You have to have a primary and a secondary to focus down. We just put them right behind each other. And I'll show you, this is just the schematic. I'll show you the real thing in a couple of slides. The other thing is that unlike an optical or infrared or radio, we're actually counting individual photons. A typical X-ray source in the sky, obviously there's orders of magnitude and variance, but a typical source might give us one count per second. So once every second we get a photon coming in. So we can't be throwing them away. We got to count each one as it comes in. So everything counts, and every modern X-ray telescope, even going back to before Chandra and XMM, going back to Einstein and Rosat, all of them are basically an integral field unit where we get both the spatial information, but every pixel we could extract the spectrum of the photons that have built up in that. Now, as I pointed out before, with the previous technology, which uses CCDs, which is basically the same type of technologies in your digital camera, we don't get a great resolution for that. So it is possible to do X-ray spectroscopy at high resolution. And in fact, both Chandra and XMM Newton have a dispersive grating on board. It's basically taking like a diffraction grating you see at the open house and passing it through that so the light just spreads out. They can do that. And they get spectra that look like this down on the right. The downside of this is several things. One, you get a very limited collecting area. So basically a very small telescope that you end up having. It's basically impossible to do this for extended sources. You end up blurring the spatial and spectral dimensions, so you can't quite tell what photon was coming from where. You have a very limited energy range that you can do this on. The point is that all of these problems can be solved using non-dispersive spectroscopy, and that's what we do. So how do we do that? This is one of my favorite slides of the talk because it sort of explains how we do this, and it's a very simple principle of what we're doing. We are essentially a single photon calorimeter. So every photon that comes in has some energy associated with it. When that hits our detector, it converts into, it deposits, I should say, an amount of heat into that pixel. We can actually measure the heat change of that photon that comes in and backtrack the energy that the photon must have had. So as I said, we're doing this for each photon as it comes in. In order to do this, we have to be at a very low temperature. So our detector has to operate at 50 millikelvin, which means we have to take refrigeration system into space because space is cold, but it's not 50 millikelvin. So we have to get down to that temperature. We have multiple stage cooling system that does this. We start with liquid helium, it gets us down to 4 Kelvin. And then we have these mechanical coolers that get us down to 50 millikelvin. And the important part is, this is not just theoretical. We have done this before. We actually got to this stage on Hitomi. This is the real plot of the temperature of the detector. Note the date down here, February of 2016. We were at about 1.8 Kelvin, switched the cooling system on, and within the space of about half an hour, we were down to 50 millikelvin with a noise level so low you couldn't see it on this plot. And we did it again. Note the date on the bottom left, October 9th, 2023. Today, I believe, is October 24th. So you're seeing real-time science being done here. 2 weeks ago, we turned on the detector again, and sure enough, in about half an hour, from about 4:30 UT to 5 a.m., we got down to 50 millikelvin again. So this is now the most exciting. Yeah, question. Good question. The total amount was something like roughly 10 gallons. It was like 37 liters or something like that. It does run out. The good news is this stage, we can do the entire cooling without any liquid helium. We can go mechanically the entire way. So it will not limit the lifetime of the mission. So you might say, why do you send it up at all? It just helps a lot with operational efficiency. If we can just start at 4 Kelvin, all we lose is just the ability of time we can spend doing science. We go from about 98% operational efficiency to something like 80 or 90. We haven't done it yet in space, so it's not that big of a hit. So we send it up with as much liquid helium as we can fit in a dewar. And when that runs out, though, we'll still be good to go. So, yeah.
Yeah, on the previous slide. Oh, yeah, sorry.
Previous slide, this one?
Yeah. So you show the time constant for the temperature to go down, which I guess is sort of amounts to your readout time. So how long is that? Do you ever have a pile up?
We do. There are sources that are too bright for us. Our highest resolution events come from things that are where the cool down time is of order like 50 milliseconds. So okay. as long as the photons are separated by it's 50 or 60. I don't remember the exact number off the top of my head, but it's of that order. As long as they're separated by more than that, we're fine. When they get closer than that, we go from what we call high res events down to mid res events, which are still pretty good. And then if it really starts to pile up for a very bright source, like if we looked at SIG-X1 or something, we would be mostly low resolution events. We do have mitigating strategies for that, though. We have filters that we can put in front of the detector to drop down the flux. We'll experiment with doing things like putting it off the focal plane and just letting the scattered light come in. So we have mitigation strategies for this. We haven't yet been able to test them out in space, but we'll figure out a way to observe even bright sources.
Oh, that's neat. Sure. Thanks.
Okay, so this is, I'll be very clear about this. This is not first light. This is a spectrum from on orbit. It's just not from a celestial source. This is from our onboard calibration source. We have a radioactive iron-55 calibration source that decays to manganese and emits this manganese K alpha line at 5.9 EV or KeV. And we are getting on orbit resolution less than 5 EV width. Our requirement was 7. Chandra, for reference, does about 150. Obviously, lower is better in this case. So very excited. We just released this publicly last week. If you follow me on Twitter, you've already seen it. So this is the only thing we've publicly been able to release yet. But I can tell you we have seen celestial sources as well. I just can't yet share them, but stay tuned. So what does this detector look like? Well, it looks like this. It's a 6x6 pixel array. That's one of our scientists holding it in your hand. The actual detector itself is, smaller than your pinky nail. These pixels themselves are, I want to say 0.5 millimeter across, something like that. So the entire array is maybe 3 millimeters or something like that. It goes down inside this entire refrigeration system. I've got a lot more pictures on a few more slides about this. But this is just a cartoon that'll show you how this works. It starts from a real picture. And I'll kind of transition into an animation. And you'll see the photons come in, hit it, different colors, different energies. The photons are actually moving faster than this. We slowed this down so you can see it. Moving substantially quicker than that. But that's basically what we're doing. You're seeing these things, they briefly light up, they heat it up, and they cool back down on an order of tens or hundreds of milliseconds. And we just stare at it for a long time until we build up enough. A typical X-ray observation might be of order a day. It might integrate for, we always work in units of kiloseconds, which if you're not an X-ray astronomer never makes sense. But for reference, there are 86,400 seconds in one day. So now you know how many kiloseconds in a day. Well, 86.4. We have a what we call an anti-coincidence detector that sits right behind the main detector, that its only point is to filter out cosmic rays. Because the cosmic ray will also light up the detector. But the thing is, cosmic rays will penetrate right through. And if they also hit the anti-coincidence detector, then we know it's a cosmic ray. We can throw that out because the X-rays themselves get stopped. This gives us an extremely low instrumental background. The fact that we're very cold and we can filter out non-X-ray events. We estimate that we have less than 1 photon per day per 10 eV bin that's actually background that somehow doesn't get filtered out. This chart, I need to update this, but we're not far enough along in commissioning just yet to be able to do this. The total commissioning length of time is going to be about 3 to 4 months. We're about 6 weeks in. So I still don't have values yet, but you can see the requirements here. Our energy resolution was 7 EV. As I said, we're measuring something like 4.5 EV on orbit, so that's awesome. The energy scale, we expect all these values to be, we don't think we're going to have any problem at all meeting any of these values. So we met them all on Hitomi, and so far everything else is looking just like that. So commission is going fantastically. We're super happy with it right now. It's a very exciting time. We see new data come in every day. So with that, here are some more pictures of what the hardware actually looks like. This opening up here, the circle in the center, is where the X-rays come through. Yeah. Oh, much worse. Yeah, Chandra is, you know, the canonical number that's thrown around is half an arc second. We're 1.2 arc minutes. So a little bit worse. The X-rays come through the circular aperture at the top. Everything you see here is part of the cooling system to get that 3 millimeter detector down to 50 millikelvin and hold it there. For size, here's some people standing next to it. It's, you know, of order a meter, 1.2 something meters tall. It's about yay big around, you know, it's a good size. This is it, hooked up with all the ground test equipment with it. As I mentioned, we do have a soft X-ray imager on board as well. It's quite wide field of view. The green up there surrounding, that's an X-ray image of SN 1006, which is not an expert in supernovae. It's almost exactly the size of the full moon. It's about 30 arc minutes across. So we could in one shot get that. So we can do large mappings of things like, you know, huge nebula and things like that that would take Chandra or XMM substantially longer to do. So every time I give this talk, I say, I need to get a high resolution version of this image. And every time I forget after the talk is over to go do that. But I think you can sort of see what it is. These are those concentric shells that I mentioned earlier. They're just layered one on top of the other. The X-rays come in this way. For those of you online, I'm pointing at the screen. This is the grazing incidence mirror that I talked about. We build them up in quadrants. So there's 4 of these. And then there's a primary and a secondary as well. This has 203 nested segments inside of it. So as I said, we build them in quadrants. So if there's 203 per quadrant, then that means there's 800 per mirror. You have to have a primary and a secondary, so that's 1,600 segments. And we have 2 identical mirrors, one for resolve and one for extend. That gives you 3,200 mirror segments. And about 25% of them don't pass quality control because we inspect every one. So we built about 4,000 mirror segments in 2018 and 2019, put them together like this. The nice part is, since we don't have to have the high angular resolution requirement, we can do this much cheaper than Chandra or some of the other things. It's also much lighter. The entire assembly looks like that. It's 50 centimeters in diameter. It's light enough that you could not easily pick it up, but you could pick it up off the table. So not the heavy hundreds, or I think the Chandra mirrors might have even been over a ton because they had to be so thick. This is actually taken at Goddard just before we delivered it to Japan. We have an X-ray beam line that shoots the X-rays down 100-meter long beam line, and we can calibrate the thing. This is going in, and this is just kind of looking straight at it. And you want to emphasize we're very safety conscious in NASA. We stencil on things like "do not drop." I don't know if anyone was thinking I will drop this unless it's written on there, but now they have no excuse. This used to be the best part of the talk, but now we've launched, so this isn't even that interesting anymore. But here's what it looks like. It's about 7 meters tall. Focal length is 5.6 meters. When you add in the other stuff, it's 7 or 7.5. 2.3 metric tons, so that's about 5,000 pounds. This was part of a VIP visit February of this year. So we had the NASA administrator, deputy administrator, the president of JAXA, the president of ISAS, which is basically the astronomy wing of JAXA. Had some high-level meetings in Tokyo, and they took a field trip up to Scuba Space Center to see the full thing. Most of the integration was done at Scuba Space Center just outside of Tokyo. Earlier this year, it's shipped down. You put it on a truck and drive it from Scuba Space Center down to one of these ports right here in Tokyo Bay. Then it gets onto a boat and ships down here to Tanegashima Space Center, which is just this southern island off the coast of Kyushu. This was us at XRISM or at Tanegashima Space Center after we'd unpacked from the shipping container. Did a lot of checkouts there. Everything you see on the right is just support equipment to test it and make sure everything's still working. Then, as I said, last month on September 7th, we launched. We were actually supposed to launch in May. There was a completely unrelated to us rocket failure that JAXA had. They were testing out a new rocket in March. That unfortunately didn't work. So that basically grounded the entire program and had nothing to do with us. So we just sat in the vehicle assembly building for 5 months while they finished that investigation. They certified this rocket, the H2A, which was not even the one that failed. But again, you have parts in common. You want to make sure that if one rocket didn't make it to the sky, that the next one will. So we ended up launching. We were supposed to launch on August 26th. We ended up having to delay for weather. I was there. If anyone comes to dinner, I can tell you the story, but I was there for that. And then it became very clear that there were 3 typhoons in the Pacific headed our way. So we were like, we need to back up into the building for a little while. So we ended up spending about 12 days due to weather delays. I had to come back to the US. So I watched the launch on the TV just like everyone else did. But this was captured by one of our engineers who happened to capture this sonic boom cone just as it was happening. We had a rideshare partner called SLIM, which stands for Smart Lander for Investigating the Moon. I don't know much else about it. You can look it up. But it was basically, it sat on the bottom of the fairing, and we were on top. It went on to the moon. I showed this earlier. This is the Hitomi spectrum of the Perseus cluster. The reason I'm showing it again is to emphasize the fact that we were not anywhere near full capabilities. I know most of you are an X-ray astronomers, so don't you look at this and say, well, does Perseus just not have any low energy emission? Like it completely shuts off there, on the left side. That's not true at all. Of course it does. It's just that we had a blocking filter in place. There's something called the gate valve is what we call it. It's just a filter that when we put it together on the ground, we have to be in vacuum. We then close down this valve and lock it off to maintain vacuum for the ground tests. We don't open that again until we get on orbit. That actually blocks all of the soft X-rays. We still have not yet gotten to the point on XRISM where we've opened that. It's scheduled for early November. So late next week or early, whenever I think it's like November 4th or something is the date. What that'll do is that'll take a spectrum like that and turn into something like that. It literally blocks off all of the soft X-rays, but there are orders of magnitude more soft X-rays here. Notice that the iron line isn't affected too much. It's about a factor of 2. I didn't worry about that factor of 2 here when I plotted it, but the important point is we'll actually be open to the entire world of soft X-rays when we open the gate valve. Here are a couple other just science simulations that I've thrown in. This one is a supernova remnant, Tycho supernova remnant, which was the supernova of 1572 AD. One of the last, Kepler was the last one definitely seen in our galaxy with human eyes in 1604. This was the one right before that. Believed to be a type 1a supernova, almost certainly a type 1a. It has an expansion velocity of about 5,000 kilometers per second. So if you look at these lines, you might say, those lines look broader than the ones you just had in Perseus. They are. You're actually seeing the kinematics here of this thing expanding at 10,000 kilometers per second, front to back. We believe, and we're actually going to do this, we're going to point right down the center of this thing, and we believe we'll see the entire spectrum basically shift into 2, one red shifted and one blue shifted, and we'll be able to do the individual kinematics on both of those. Here's another example. This is a famous picture of M51, optical and X-rays overlaid. There's a lot of sources in galaxies and next supernovae. Pick your favorite one, whatever you happen to study. This is the actual Chandra spectrum of M51. And with XRISM, we'll see something that looks like that. So again, just imagine how much more science we'll be able to do when we do these models, or when we model data like this. And in fact, this came up at lunch. It's going to be a challenge for our atomic data knowledge, because we're going to have lines and line ratios we've never actually been able to measure before. We've only been doing a theory. I'm positive some of them are not going to fit. I'm more excited about the ones that don't fit, because that means we're going to be learning something new. If we launch it and see exactly what we expected to see, it's nice, but we won't really be learning new science. So this is really going to be a revolutionary thing. Yeah.
Is it possible to apply?
Oh yeah, absolutely. I'm going to get to that in a couple slides, but yeah. In fact, the call will be coming out in a couple weeks. This is a famous AGN in NGC 1365. Again, a current spectrum on the top right, that's the X&M spectrum. And we can certainly see absorption lines in that. That's how we learn a lot about the torus and the other stuff that's around the AGN, is we have this bright source shining through a bunch of gas, and we look at what the absorption lines are. With XRISM, we will have the resolution to not only obviously see those absorption lines, but we think we'll actually see scattered emission, scattered lines in emission off of the outflow of the stuff reflecting off of the torus. So it'll be a completely new measure for the dynamics of the AGN wind, to be able to compare both the absorption from stuff that's blocked and the emission from stuff that's basically scattered off. You can learn about all this and more in our white paper that we put out a few years ago. We thought it would be useful to just have one single document. As you can see from the table of contents, it's about 30 pages long. So we tried to kind of cover all of astronomy and just a broad overview of what this can do for your, whatever your astronomy is. So you can sort of see everything there. We even talk about exoplanets. If you want to hear what we can do for exoplanets, go read that. So mission timeline, where are we right now? So going back to just before COVID, November of 2019 was when we finished up what we call the calorimeter spectrometer insert. That's basically the heart of the detector. That was all built at Goddard and shipped out to Japan just a few months before COVID hit. People often ask, how do you get it to Japan? United Airlines. Quite serious. Yeah, United Flight 803. Been on it many times from Dulles to Tokyo. You fill out a lot of paperwork. They let you actually go down into the cargo hold and make sure it's there, and then you can go back when it arrives in Japan. They meet customs officials to bring it off. It does not have to go through baggage claim. The white paper released in March of 2020. The final selection of PV, which is performance verification targets. Those are the targets that we're going to observe in the first 6 months of science operations. After that 6 months is complete, to answer your question from earlier, that's when we'll go and do a full geophase mission. And the entire rest of the mission will operate like that. Just annual calls for proposals. Community tells us what you want to observe. We'll set up a TAC. Oh, the X-ray mirror assembly. So that was delivered in fall of 2022. Both of those were completely built, integrated at Goddard, and then we shipped them over and they plopped them onto the top of the telescope. Launch, we've covered cycle 1 geo call for proposals. Will come out in early November. The deadline for that, skipping ahead just a little bit, is right here. We're targeting a deadline of February 22nd, 2024 for the cycle 1 call for proposals. We'll have a special session of the AAS meeting where, if everything continues to go well, we will probably be able to show some initial results from that. So pay attention to that. We'll also have a booth presence at the AAS. This is a big one. If you're interested in learning more about some of the data analysis, how you might write your cycle 1 call for proposals, we're going to have a workshop at the University of Maryland in January. It'll be both in person if you want to come and hybrid. We just secured a venue for that last week, so I don't have the website up yet, but we'll have a website. We'll announce it through, whatever newsletters we can. So special session again at the head meeting in April of 2024. And then again, if the schedule continues, cycle 1 observations will start probably right around the middle of 2024. Obligatory slide on how COVID impacted us. As I said, we delivered the Resolve instrumentation just before COVID. We had a team over there when COVID hit. They had to come home. Japan was actually completely closed to foreigners for about 2 years. Basically, even if you just wanted to visit Mount Fuji, you couldn't go from March of 2020 to they reopened in October 2022. So about 2.5 years. Well, we were actually able to get team members to and from Japan throughout that. It took extraordinary effort on the parts of not just NASA, but the State Department of the US, the Ministry of Foreign Affairs in Japan. It was kind of our running joke in the team that the emperor has to approve all travel. It's not entirely true, but it's not as far off as you might think. It went pretty high. But we were able to get something like of order 100-person trips to Japan in that time period for both our scientists and engineers, because again, we built the instruments, so we need to be the ones there helping out with the integration and testing. You don't want to do that over Zoom. Like, okay, put the red wire over here. No, nope. So it was vital that we had that ability to go there and participate. The first year or so of people going was extremely onerous. They had to quarantine for 2 weeks upon arrival in a small hotel room that not much bigger than like this section of the room right here. 3 times a door, people would bring food to 3 times a day, people would bring food to the doors. Thankfully, all that's over now. We can actually travel freely. And we actually were able to have our first in-person science team meeting since 2019 in late 2022. So the GEO program, since you asked about it, I've covered a lot of this. After the commissioning and the PV phase, the rest of the mission is in that GEO phase. Aside from regular calibration time, we don't reserve anything else that's proprietary except for those first 6 months. Everyone in this room, if you're writing a proposal, will write to the NASA solicitation. There will be simultaneous ones from NASA, JAXA, and ESA. Which one you go to just depends on where you're located, and I assume everyone's located here. Let's see. We'll have a small number of objects that we'll release very early on, just so people can see what the initial data looks like. It'll probably be a limited release of just certain parts of the data. But we're going to try and get that out. We will get that out before AO1 so that you can see real data before writing the proposal. And we will have some funding. We actually have a pretty generous funding profile for US-based scientists. That just means you're at this institution. It doesn't mean what your nationality is. If you write a successful proposal as PI, you will get a pretty good amount of funding that goes along with that. And we also have opportunities for laboratory astrophysics work. That could be, I have a lab that does atomic physics and I need money to run this experiment. We have some money set aside for things like that. It could be, I have a lab and I want to build an instrument that does atomic physics, or I'm a theorist who needs money to support my theoretical calculations. We have that built into the call for proposals. I won't go too much into this. This is just the logistics. A lot of this I already covered. You can actually see the breakdown of time. NASA will get 44% of the time. JAXA will get 48%, and the Europeans will get 8% of the time. Again, as I mentioned earlier, if you're hearing this talk, you're almost certainly going to be submitting to the NASA solicitation. You can have an international team if you want. It's just whoever the PI is, that's where that proposal will go. A few limitations in cycle 1. We're not going to have joint observations yet. We will almost certainly start those in cycle 2. So we'll have joint observations with New Star and Chandra and JWST and all of those things. We're just not going to do that in cycle 1. And we're also going to not allow generic TOO targets. Like whenever a supernova goes off, can I observe it? It needs to be a little more specific than that for cycle 1. I'm going to skip this slide because I talked about this. We're just going to put out a couple of early science observations, early release observations, so the community can see what these will look like. And this is pretty much the end. I just want to advertise that if you are at the stage of postdoc, we have some funding for NASA postdoc program fellowships to come to Goddard and work on XRISM. I've purposely wrote this as vaguely as possible. I just say the successful applicant will carry out a research program in any area related to the science. So we can be pretty broad. I would say most of the things that are in astronomy, we have people at Goddard that do that sort of thing. So, you know. And I'll finish just by having some websites up where you can get more information. There are sites both in the JAXA, NASA, and ESA. And finally, I'll just say closing thoughts. Again, high resolution X-ray spectroscopy really is sort of an unexplored space. We have not ever had these capabilities before. So I'm excited. I'm excited about the unknown things we'll learn. I'm excited about the unknown unknowns that we don't even know that we will learn yet. I think this is really pioneering technology. Those of you who keep up with things like telescope development know that most of the future, if you think long-term in the future, these capabilities are going to have to be tested now in order to fly then. So I will end there. I'm happy to take any more questions. Again, thank you for having me.
Hey, thanks very much, Brian. And just a note that Alex will be hosting dinner. So if you're interested in joining them for dinner, please meet Alex right after the talk.
I almost forgot. I brought stuff. I have, for those of you online, I'm sorry, maybe someone can grab some for you. We've got little lapel pins. We've got various stickers. I've actually got 2 different types of stickers. You can see it. There's one of them on the back of my laptop here. So I'll leave these out here. You can come up after the talk.
Get both pins and stickers.
Yeah, absolutely. No, I mean, these are great to hand out if you guys do outreach events at schools, whatever. So
Or if you run out of candy on Halloween.
exactly.
So what kind of with the anti-coincidence detector, do you just get counts, or do you also get energies for the cosmic rays?
I don't, that's a good question. I think it just lights it up and we just know that throw that event out. I don't believe it detects energies. Yeah.
Thank you very much for the talk. I hope you'll forgive us fairly naive question. With the cosmic rays and such, I know for other kinds of detectors, cosmic ray gets it bleeds over into other pixels. Is the same true here, or is it just a single? Is there relatively large? Is it a single?
I don't know for the cosmic rays. I know that sometimes with bright enough sources, the X-rays themselves can I mean, our point spread function is larger than a pixel, so everything lights up more than one. But we can have things like crosstalk, electronic crosstalk. We believe we have ways of filtering that out, of basically fixing that in the pipeline processing. So my guess is the cosmic rays probably do the same thing, but I think we could filter that out. Yeah.
Can you just say a few more things about how these micropolarities actually work? How do they measure temperature with such accuracy?
Yeah, well, let me see if I can go back. So this is probably this is a better slide here. It's basically just a calorimeter. It's just a thing that we have a fixed temperature. We cool it down to 50 millikelvin. You saw from the noise plot that it's when I say 50 millikelvin, I really mean 50 millikelvin. Like it's, God, I didn't think it was this far back. What was that? Oh, now the animations, come on. Yeah, let's do it this way. Here it is. It was this slide. So yeah, I mean, we are really accurate in the known temperature that we have, which means any photon that comes in, and it just imparts a few extra millikelvin. So maybe it takes us from 50 to 55 for 10 milliseconds, and we drop back down. We're just measuring that heat change. So it's just basically attached to a very accurate thermometer. And it's just basic physics at that point to back, because all of the energy of the photon goes into that heat. So you can just do the conversion from heat to energy, and there you have it. It's very simple, but incredibly difficult to actually build. I mean, right now, Goddard is still the only place in the world that can build this. Other places are beginning to do it too, but it was developed. The idea actually was developed in the 80s, and it was developed in literally a hallway conversation between two folks at Goddard. One of them was building infrared bolometers, which is kind of a similar technology. And another guy, Rich Mashotsky, was talking to him and said, I wonder if you could do that for X-rays. And they literally went to a drawing board, kind of worked out some basic math and figured out, you know, if you could get the temperature cool enough, it's physically possible that you could do this. And in the 90s, the development continued. We've built this a couple of times now. As I mentioned, we've had a little bit of a trouble past with this mission, but we do know how to do it.
Question. So you said you put the telescope orbit around the Earth, right?
Mm.
So what's the benefit of that over putting it in altitude?
Yeah, that's a good question. What orbit you choose is always a question for any telescope. The simple answer for this one is because this was put in low Earth orbit because the previous one was put in low Earth orbit, and we're not going to go redesigning the mission at this point for a quick rebuild. As for why it was initially done that, you know, L2 is a relatively recent phenomenon. It requires a much bigger rocket to get there. So it's more expensive. You don't have as much, the communications are different. So, you know, I don't know why in previous versions of this, it was chosen to go in low Earth orbit, but I think the simple answer is it's probably just simpler when those missions were originally conceived to do that. There are also, I'm just thinking in real time now, for X-ray missions, there are trade-offs between low Earth orbit and L2. Low Earth orbit is actually a better orbit to be in terms of radiation. So that basically would raise your background level if you were at L2, because basically the Earth's magnetic field protects us from a lot of these cosmic rays and solar wind particles that come in. So X-ray missions really have to think hard about what it is you want to do. So, yeah. Yeah. I heard him earlier when he was asking a question.
Brian, you're good to go.
Oh, thanks. Yeah, thanks, Brian. So,
I guess I could say that. Go
um,
ahead.
yeah, so you may have already said this, but you say a bit about the energy range you're sensitive to and what sets the high and low limits?
The energy range is very similar to Chandra at XMM. We go down to about, we have response down to about 0.2 keV and up to about 12 keV. We actually have some response that goes up to like 20, 25, but it dives off so quickly there. You'd have to be looking at something extraordinarily bright to get meaningful signal above 12 keV. So everything has to be an optimization. We could have optimized it differently, but I should put an effective area curve or response curve in this plot for future reference. You can Google it online, just Google XRISM effective areas, what we call it in X-rays. But we basically optimized this to peak at around the iron K alpha line at 6.5 keV.
Sure.
So,
yeah, cool. At high energies, is it just that there's not much flux, or do they stop leaving all their energy in the detector?
That's a good question. I suspect it's the latter, but I can find out and try to get back to you. My suspicion is it's the latter, that they probably, I think you can design the substrate to be able to capture various ones, and we could have designed it differently to focus on hard X-rays, but then it probably wouldn't have gotten the soft ones. So
Yeah, sure.
it's just optimized for this band.
Sure. Cool. Thanks.
You said there were a couple online. Is there an next? Oh, okay.
I have a good question myself, actually. So, I don't know what has been coming out of Rosita, probably not much because it's shut down.
Yeah, nothing lately.
Has there been any new sources discovered by the Rosita survey that are going to be interesting for PRISM to follow up on, or has it really been maybe not a big impact on your science program?
I'm sure there have been new sources. I mean, eRosita has done at least one iteration of their all sky survey, if not two. I mean, they were expecting to do a lot more by now, but as you said, they haven't been operational in 2 years. For those of you who don't know, eRosita is a mission that's a partnership between primarily Germany and Russia. There are other European member states that have a stake in it. I don't have an exhaustive list off the top of my head. It's not a NASA mission or not a JAXA mission. As a result of the war in Ukraine, it's basically been shut down since that started. But it did do at least 1 or 2 passes of its all sky survey. I don't think they've released that yet. So I don't know the answer to that. But I'm sure they have source catalogs that they will be releasing at some point. In the X-ray sky, we generally know the interesting objects by now, but certainly if there's something that comes up, or if a time domain event comes up, we'll have response capabilities. We're not swift, we're not going to get on it in minutes, but if something interesting goes off, it was unknown before, we'll point at it.
Yeah, go ahead.
I was just curious, how you mentioned it can only be created at Goddard. What is the actual technology that Goddard uniquely can produce? Is it the keeping the cryogenics, or is it like some other component? Does that question make sense?
Yeah, and in this case, it was everything. I mean, and there are other capabilities elsewhere now for doing things like cryogenic systems, but the original one was developed here, and the actual detector technology itself. I'm not a lab person, so I can't tell you in detail what they are. But yeah, they were all developed there.
Hi, thank you for the talk. So what's do you have the optical theory and population for
Oh, like going around the Earth? Yeah. The problem in low Earth orbit is half of every orbit, the Earth just gets in the way unless you're pointed straight up or down at one of the ecliptic poles. So I think the best way to answer your question is our overall operational efficiency in terms of time we'll be pointing at a science target divided by just wall time is about 45%. So again, with 50% of it already being taken out by the Earth, we're pretty efficient once we're actually able to be somewhere. Not meaningfully unless you got very far out, like if you got to like L2 or something like that. And we don't have the capability right now to increase I mean, it's in orbit, and now we don't have another booster on it. But going from 577 kilometers to 677 kilometers, I mean, just draw out a picture of the Earth and then draw another circle on top of that, scale them up, and you'll see it's not much different. You have to get really far away to start to make a meaningful effect.
Okay. Yeah, the students can stick around for some calculations on it.
I think you all just got to do homework assignment.
Okay, so yeah, don't forget to pick up some of the freebies up front, and let's thank Brian again. And let Alex know if you're able to join the dinner.